All right, we're going to go ahead and start with Lesson 7, the uncertainty principle. Now, it should be very clear to you that according to the Bohr model, the electron can only be at specific distances from the nucleus, and those distances are principal energy levels or shells. And each of those principal energy levels or shells has a fixed quantity of energy, and that is including the electrons that are in those shells. They also have fixed quantities of energy. And so according to Bohr, we should be able to know the position of the electron in the atom and the amount of energy or fixed quantity of energy that the electron has. However, when Bohr began to apply the same mathematical equations and principles to more complicated atoms, even helium, he began to realize that the mathematics didn't work as well as it did with hydrogen. There seemed to be some problems. This was very puzzling to Bohr and was uncertain to why this was the case. Why did his mathematics and the ideas of the Bohr model work so well with hydrogen, but not so well with the other atoms? To begin to understand what the problem is with the Bohr model, we have to look at Louis de Broglie. Louis de Broglie, a French mathematician and physicist, began to theorize in 1925 a very possible explanation to why the Bohr model has some problems. And in his notion is he believed that if light could behave as a wave as well as a particle, maybe electrons themselves not only behave like particles, but might also behave like waves. Indeed, that is the case. An electron has both a wave properties as well as particle-like properties, just like light does. Now, this revolutionary idea became, because it is linked to particles, properties of the electrons, its mass and its velocity, and wave-like properties, there's soon to be experimental proof that this was the case. Now, this went beyond that. In fact, what de Broglie understood is that not only just electrons or photons can be waves, but also other matter, such as you and I, or planets, or apples, or, well, anything that has mass might also have wave-like characteristics. And indeed, that is true. We understand that to be true today. However, the more massive an object is, the less likely it is to appear to have wave-like properties. So a small particle, like an electron, having very, very little mass, it is going to also have very distinguishable wave-like characteristics. So at this point, we need to understand this important idea. Just like a photon, which is a particle of light, light also can have wave-like characteristics, and that is the wave-particle duality. The electron is in the same boat. It can be a particle, and sometimes it can be just a wave. It can be both, or it can be neither, or one or the other, okay? I know that just like with light, it's pretty interesting, okay? So here we have a photon. Remember, a photon can also exhibit an electromagnetic wave property, which light is. An electron, then, according to de Broglie, can also be not only a particle, but also exhibit a wave-like characteristic properties. Now, this leads us to a new principle of understanding a very important scientific principle called Heisenberg's uncertainty principle. Now, if it is true that the electron in an atom is also a wave and not just a particle, then it brings some interesting problems to the electron. Problems that Warren Heisenberg began to understand. Now, because electrons behave as waves in atoms, Warren Heisenberg concluded that it was impossible to know the position of an electron in an atom and its energy with any degree of certainty. So therefore, this became known as the Heisenberg uncertainty principle. Remember, Bohr understood this, or the Bohr model associated the electron with this. We understand the position where the electron is located at and how much quantum energy it has. But with the wave nature of the electron, this is thrown out the door. Because if we look at electrons behaving like waves and not particles, then we cannot know the exact position of an electron and the amount of energy that that electron is going to have. So, Heisenberg said, hey, we can know one or the other. We can either know the position of the electron and then have maybe a somewhat of an idea of how much energy it has, or we can know for certain how much energy the electron has, but only a probability or an uncertainty in where the electron is located at in the atom. So what we have understood today, in today's modern model of the atom, is that using Heisenberg's logic and theory here, is that we have decided that we are going to know how much energy an electron has at any given time. So we'll know how much energy the electron has, but what we won't know is its exact location in the atom. All right? So based on Heisenberg's idea, if we choose to know the energy of an electron in an atom with certainty, in other words, how much quantum energy the electron is going to have, then we must accept a correspondingly large uncertainty in its position in the space around the atom's nucleus. We can only know the probability of finding an electron with a given energy within a given region of the atom. And so that concluding remark there about the Heisenberg's uncertainty principle is pretty dang important, okay? So this is it for this lecture video. It's very short. Make sure that you come away with understanding what the Heisenberg uncertainty principle is and what its meaning is with the electron, as well as understanding that the electron not only has particle-like properties, but also has wave-like properties, which results in the uncertainty principle. All right, so that is it for now.